We are a little bit ahead of our schedule, just 3 minutes. But the next speaker is Jasper Wuister from DHV, Royal HaskoningDHV. In fact, Jasper Wuister, he had his degree from Delft University of Technology, from the Delft Center for Systems and Control. And afterwards he worked for, it was Siemens, wasn't it? And then he changed jobs to DHV, and without changing jobs, he changed company, yeah? Because DHV and Haskoning, they merged a few months ago, so now he's a worker of DHV HaskoningDHV, and then Royal, then you get it for free. And his presentation is about plate aeration modeling and soft sensors that you developed for the operation and the control. Okay.
Yes, thank you. I'll put the microphone up. Thank you, Luc, for your introduction. When I submitted my abstract this spring, I thought the results of my activities on plate aeration monitoring with soft sensors would be very interesting to present to you. So that's why I named it Plate Aeration Monitoring with Soft Sensors, which makes sense then. But during the rest of the project period, it became clear that plate aeration was a typical example of the results of our SLIM project, which I'm working on, which is much more on what the subtitle says, water quality models as a communication tool to facilitate the dialogue between operators, plant operators on the one hand, and researchers, water researchers on the other hand. So plate aeration will actually be at the complete end of my presentation, and I will take this opportunity to tell you more about the SLIM project in general and what the conclusions so far are. So what is SLIM project? SLIM is an acronym, of course. It stands for Self-Learning Integrated Model-Based Management, but I think monitoring is much more appropriate for what we are doing. It's an Innovator project, and we have 6 partners working on this project, with VTENS as the most important launching customer, Yorkshire Water in England, the Delft University of Technology, Perceptive Engineering from the UK, Logisticon, and Royal HaskoningDHV. And what is SLIM aiming for? SLIM is aiming to improve real-time water quality information to the operator, doing so by estimating and predicting water quality based on drinking water quality models. And this can be data-driven models or physical chemical models. Thus improving plant operation on the one hand, and improving these water quality models on the other hand. Well, that's a bit formal. What I think it is about is bridging the gap between operations and research. So what do I mean by that? An operator is working constantly on the process that our researchers are researching on. And what they do, they take in the measurements from the process, and they interpret them. But the measurements in the process are generally cheap because they have to be maintained, and the information from these sensors is in general very limited. So the view of the operator on his own process is very limited, because he uses just the ordinary sensors that are there in the operational process. On the other hand, there is the water researcher working in his laboratory, coming up with all kinds of difficult formulas. We have already seen a few of them a few presentations back. And this researcher is gaining extensive knowledge in the process and the treatment processes at hand. But the problem of a researcher is, in general, he only has his laboratory and not a full-scale pilot plant to work on. And the strange thing is, these are 2 people working on the same process. So why not connect them? And IT is, I think, a beautiful way to connect people by providing the information the researcher has to the operator. So not only bring the operator sensors, but also bring him the kind of soft sensors that are derived from software, and bring the results of the soft sensors in the full-scale plant back to the researcher to see whether the models are valid. So how do we intend to do this within the SLIM project? Bringing information to the operator is in general a difficult thing, because reporting, which was already mentioned in the previous presentation, is a way to bring information to the operators, but operators in general have limited time and do not tend to go through all kinds of reporting. So we decided we would make a dashboard, much like the SCADA system the operator is familiar with, but then include this information from the soft sensors. So where is this information on this dashboard for the operator coming from? I think I have this. Yeah. Two types of models, black box models and white box models. And within SLIM, because we're working with drinking water, we chose the Stimela drinking water model platform of the Delft University of Technology, and the perceptive engineering solutions for data-driven modeling. But in general, you can use the systematic with all kinds of modeling solutions. Actually, we now use as a kind of white box platform the Freak-C geochemical models. And we have three data sources. We have the lab data, the real-time experimental data, and the plant data. So the plant data, these are the things that the operators used to looking at. The real-time and the lab data he is used to receiving in reports, and so he can check if what he has done in the past has worked out or not. But probably this has been a few days or even a week ago. So it's of limited use for real-time control. This real-time information, that would be very interesting to know, but is often experimental or pilot installation, things like this. Ooh, why doesn't it work? Okay. Wrong button. And within SLIM, we have three sources for this information. So there's the laboratory information management system that is already in place, the real-time plant system that is already there too, and we introduced this experimental real-time data source, which we call the SLIM box, which is actually a rather extensive set of analyzers built on platforms so that they are mobile. These are the real hardware sensors, the ones that are most of the time way too expensive to install in a plant for operational purposes, but we use them to gain extra data from the process temporarily. To give you an idea why it is a very bad idea to put these sensors in the process all the time, we have like 1 or 2 people full-time working on cleaning these sensors. So that is another reason why soft sensoring is a very sensible thing to do, because it's impossible to measure like the iron concentration all the time with this device, because you need a person standing next to it cleaning it all the time. Alright, so this SLIM project in practice, I already mentioned our launching customer, which is Vitens, and our pilot plant is in Oldenholtpade, which is in Friesland, in the northern part of Holland. And we decided to dig into 4 of the treatment steps at Oldenholtpade, which is the raw water extraction, the plate aeration, there it is, rapid sand filtration, and the softening. So for those of you who are not from Holland and may not know Vitens, this is our planet. You're approximately over there right now. Vitens is the largest drinking water supplier for the Netherlands. It operates in this area, mainly the northern and middle part. And Oldenholtpade is over there. It's a small Frisian village. And from Google Maps you can see it looks like this. It is very beautiful and quiet. And on paper, in a diagram, it looks like this. So we have the groundwater extraction, it's a groundwater pumping station, plate aeration, rapid sand filtration, tower aeration, pellet softening, rapid sand filtration again, and then ion exchange color removal. And as I said, we are focusing on those 4 treatment steps, although we are thinking about including tower aeration, because then we have a kind of treatment train for 5 steps in a row. And we try to develop these soft sensors to provide this extra information to the operator by means of the data-driven soft sensors, the white box soft sensors, and what we call grey box soft sensors. So soft sensors that are based on rules of thumb, or they're not completely based on physical chemical equations, but need some data-driven tuning, but rely on physical chemical known relations. And what I'm going to show you is just a few of the things we have developed already. And I'm not going to dig deep into the data validation and the whole process, what we did, because the message I want to put forward is the way that operators and researchers can both benefit from these kind of soft sensors and models. So these are the way the dashboards at this moment look. They are not really sexy in the graphical sense. And we really built them to figure out what information do we want to present, and they are very easily changed during the process. So this is currently our only data-driven soft sensors developed by Perceptive Engineering from the UK, and we are estimating the iron concentration at a given moment in time at the rapid sand filtration. And we estimate the pH. So this is what you see here on the soft sensor. So excuse me for the language. This is one of the things that are the obstacles on the bridge. That operators often talk the local languages and researchers often speak English. So this is in Dutch, but I'll guide you through it. What we intend to put on these dashboards are the pure facts from the soft sensor. So the model estimations. On the one hand, the available measurements that are already being done in the process, and some kind of way to tell the operator how he is doing, how is this process working. And in case of the rapid sand filtration, we can choose the iron concentration, for example, as a way of telling how well the process is doing. Well, these kind of slides are in between, so the models are very good, and that is because researchers have made them. So in this case, Perceptive Engineering is very good in estimating process behavior based on pure data. But what you can see already is the problem with data-driven sensors, that if something happens that the data-driven model has not seen before, it is not able to estimate well. But I mean, in general, I think the rapid sand filtration soft sensors are proving themselves as being quite accurate soft sensors based purely on data. So with the measurements from these slim boxes, the lab measurements, and the pure process data are enough to make a model without any physical or chemical knowledge, which is able to predict this rapid sand filtration process in this given situation, of course. And why are these soft sensors useful? This is something we learned from the rapid sand filtration experiments as well. What you see on the right, I hope you can see it with the green, is the laboratory results over a long period of time, which are available for the rapid sand filter. And well, they go up and down, and we have currently no clue when there is a high amount of iron, because that's what you see on the left, the amount of iron in time. When there's a high amount of iron, is it due to the fact that there has been just been backwashed, so that there is some ripening of the filter, or that is just a badly working filter. When we, on the other hand, use the Slimbox measurement, which has an online iron analyzer, we can see in real time the way iron works in one filter batch, which is what you can see over here. And you see nicely the process of ripening of the filter and then going steady. But this is a very expensive measurement device. This device is the one that we need a person standing next to it to clean it all the time. And what the data-driven soft sensor does is estimate or predict the outcome of this very expensive and difficult sensor. And it does that in quite an accurate way, in a way that tells more to the operator in terms of where's my filter and how's my filter working than the lab measurements on the right. Let me see, how's my 2 minutes left. I was afraid so. So with Stimela we can do the same thing, but then based on physical chemical models. So this is the model of the raw water extraction, which is the freak model for pH and EGV, and just a flow proportional mixing for the others. I'll do not bother with the details. This is all model validation. White box soft sensors for the pellet reactor, which we're currently validating dynamically, but these were static validation results. And I have 1.5 minutes left, and I still have not said a word about the plate aeration, so here it is. I put an extra photo in because it's the presentation title. The plate aeration, we found something very different. Up till now, you've seen we told the operator the results of the modeling. And so this is mainly beneficial to the operators. But with plate aeration, we had a problem. Because plate aeration is about methane removal, and we wanted to predict the methane removal so we could predict when the plates needed to be cleaned. And the problem is, we also measure CO2, and when the amount of the methane removal is correct, the CO2 removal is not. And we could not make the model predict the true process in a correct way. And we did system identification, and the result was there should be a huge amount of recirculation of air inside the plate aerator to be able to fit the model to the actual measurement results. But then Alex, who is Alex is the one who made the Stimela plate aeration model, already responded to my abstract that this could not really be true. So this is the invitation of the operators who are actually seeing this to the researchers to make the model fit to the real process. So that's what SLIM is about. It is about bridging operators and researchers. And soft sensors is, in my opinion, a great way to do it, because you can present the result of years and years of mathematical and data-driven modeling to the operator, which can increase the operator's insight in the process, and on the other hand, give full-scale model results back to researchers so they can more easily do their model validations on full-scale data. And this is only possible because we can make this IT environment an integrated environment now, where all systems, whether they are from the scientific part of the world or whether they are on the process automation part of the world, we can integrate them in one platform and bring operations and research together in this fashion. That is what I wanted to tell you about the SLIM project. So I hope you have questions.
Thank you very much, Jasper. Are there any questions? Yep.
Quevedo from Barcelona Tech University. When you use the models need initial conditions. For example, turbidimeter. You expect to which is the value of the turbidity in the future. but you need the initial conditions, and then you use the real data or the turbidity. But what happens if these turbidity measures are grown at bad data? Then your estimations in the future is grown also.
Yeah,
no?
That's completely correct. And initial condition estimation is one of the major things we need to take care of in the bringing the models to the actual plant. What we besides what I've shown you here is just presenting the model results to the operator. There's a simultaneous process of data quality monitoring, which is the data-driven part of it, which is also the perceptive engineering part, which constantly evaluates the statistic relations between the different parameters. Mm-hmm. And when there's a breach in this correlation, then this data quality monitoring sends an alert to say the value that I'm getting now is not a reliable value. And it does this on the hardware sensors, and it also will do this for the software sensors. Mm-hmm. And I hope this is a way in which we can detect at least that we have an incorrect estimation.
Second question is, with these models, to predict the next step is quite easy. The problem is in the future. Then turbidity. You can say 1 hour later or a few seconds later which is the turbidity. But to say which is the turbidity for the next week, all the next weeks, is a problem. The models are not precise. And then the deviations is increased. It's the same than the weather, no? In 2 minutes, sure, it will be sunny day. But tomorrow or in the next month, and then which is your predictions? Which step, when you present the results, very good results, you predict in the future only one step, and you present the real results with the estimations of the model only one step, infinite steps in simulations mode, or how?
Well, this is the thing we want to gain insight in with the SLIM project. How long can we rely on model predictions before the real world and the model start to deviate too much? And are there mechanisms we can use to bring them back together? So in the case of this data-driven model, I myself was rather surprised that after, I think, 4 months of continuous running, the model still had comparable accuracy as it had the moment we validated it. But there is especially when process conditions change, the model will surely deviate. And well, we're trying to figure out a way of detecting that. And I already said the data quality monitoring is one of those things, but it's really something we have to gain some experience on, because at least in the Netherlands there's not much experience on running models together with the process for such a long time in real time.
Is there another question? I had a question a little bit in the same neighborhood as you had, because there is for example, part of it is black box modeling. The one thing is that you said, okay, you can run a black box model without knowing anything about the process. I'm wondering whether you can do that, because you have to select at least some data where you are going to fit the model on, and that you need some experience, I think. But the second is, when you use a black box model, in fact you are not modeling the process, but you are modeling the operator. Because when you have operational changes, or when the operator is always performing suboptimal, with your model you will never have an optimal situation. And so my question is, what are you doing? Does it help to find the optimum when you're only measuring or let's say modeling the operator, or should you have another way of validating this type of model to be able to have a broader range of data to be able to select the optimal?
Well, I agree. When you speak of optimization, then data-driven, a model which is developed by data-driven techniques only tells you what it has seen in the past. So it is a very good tool for things like data quality monitoring and things like just predicting the current mode of operation. But it has very limited use in questions like, can I increase my filter run with 10 hours and will I still have the appropriate amount of iron removal? Things like this. You can use the data-driven model to give you an idea on which way, based on the dynamics that the model has seen before, which way it will go, but it will never be a very reliable estimation. So when you're looking for optimization, the white box approach is a much more sensible thing to do.
Okay. Thank you. Other questions? No, then we're going to the tea. 2 minutes over time, so not that bad. Thank you once again, Jasper.
Thank you.
Okay, and then we have a tea break now, and then there's once again a poster presentation at the poster room. So I invite you in 20 minutes from now to come there. Okay, thank you.